Hello, I'm Michael Gayton. I'm coming to you from my home in Gaithersburg, Maryland, USA, and I work in the Mass and Force group of the National Institute of Standards and Technology. Our group is a calibrations group where we perform calibrations of mass standards, force sensors, accelerometers, microphones, and sound calibrators. Today I'll be giving you a presentation on work in our group on the topic of a dynamic uncertainty protocol for digital sensor networks. So let's get started with this presentation. I'm presenting this with my co-authors Richard Allen, John Geist, and Akko Shigioki, and we're all from the Mass and Force group. Dynamic uncertainty basically is this idea that the uncertainty of the measurement reported by a sensor depends on the excitation conditions. The analysis for dynamic uncertainty has been reported, by example, from PTB in this paper that you can find online, Towards Smart Traceability for Digital Sensors and the Industrial Internet of Things. So there's quite a bit of work in terms of developing analyses based on metrological principles for smart sensors. What we're talking about today is basically a concept for using dynamic uncertainty and a communication protocol where the calibrated smart sensor reports its measurement together with the instantaneous uncertainty of this measurement. And so this uncertainty may be different depending on the excitation conditions. And the question to consider as I'm going through this talk, and for you to consider, is whether this protocol might eliminate the need to keep or to refer to a digital calibration certificate or data sheet by the host computer in the application. Here is my idea of what I think of in terms of traditional use of sensors. You can think of having a computer that is connected to a sensor. The sensor could be reporting, for example, a voltage, and that the host computer must then convert that signal. If it's analog, it would be digitized and then converted to the actual measurement. And so the host computer must know something about the sensor in order to do that conversion. With this idea of dynamic uncertainty, we add another layer where the measurement signal is coming to the host computer. And not only is there a conversion that's going on at the host computer, but also there's an analysis that's being carried out that can then determine some kind of estimate of the accuracy and therefore the uncertainty of that signal that's being reported by the sensor. In the dynamic uncertainty application at the sensor node, which is what we're talking about here in our proposed communications protocol, is that the smart sensor now, the idea is that the analysis and conversion and estimate of the uncertainty is done at the sensor node. So you could think of a smart sensor as a digital sensor, as we might buy a MEMS-based sensor, plus a microcontroller that performs this signal analysis and communicates the results over the network. So if we take a network of sensors, and here I'm showing various sensors in this network, although there could be one type of sensor, but here I'm showing various sensors, and they're sending their information over a communications network. I'm also showing a network of host computers as well. And the idea here is that the sensors also may not just be communicating to one host computer that's interested in collecting data, but there might be others as well that are also connected and also collecting the data and analyzing it. So the accelerometer here, in this case, is sending its acceleration information over the communications network, and then the host computers can then collect this data. If we swap this out with another accelerometer, say of a different model or a different type, is it possible then that the communications protocol itself will automatically take care of any changes that are needed? And this could be then making the network more adaptable as well. So in this demonstration, the smart sensor that we used is a device that's an Adafruit Feather NRF 52840 Sense. And this is an interesting device for this project because it not only includes the microcontroller on this little board the size of, say, a thumb drive, and you can see that in a photograph of this on the left, but it also includes sensors, including accelerometers and gyroscopes. So the first thing we have to do before we can implement or demonstrate this communications protocol is the calibration. And so there are a number of calibrations that I'm listing here that we've gone through. The first one that I'll talk about is what I think of as a static measurement. You know, this device is put on a flat surface like a tabletop, and readings are taken over a period of time to determine the 2 sigma standard deviation of the readings. We've also developed in our group a calibration method that we call intrinsic calibration. You can find a very detailed description of this in the link that I'm providing here. And basically it's done by putting the device on a 2-axis rotation stage. And this rotation stage is orienting the devices turning around each of the 3 axes, X, Y, and Z axes, to determine the sensitivities. And in fact, we call this intrinsic properties because it's determining not only sensitivities, but also the angles between those 3 accelerometers. We can also apply the same approach using constant rotation. This basically is the same exact protocol, but instead of stepping through discrete angles, we're rotating at a constant rotation rate. And here in this work, I'm going to report this at a low frequency of 0.5 hertz. We also have a long stroke shaker calibration capability. And so I'm also including this as a comparison with the other 2 to show that how a long stroke shaker would compare in its calibration. And this was done in this paper using a 1 hertz excitation and using a laser Doppler velocimeter. So here we're looking at the static measurement first. And what you're seeing is a collection of data from each of the accelerometers. I have them color-coded in this graph as red, green, and blue. And in this calibration, the Z accelerometer is pointing vertically upwards. And what I'm plotting here is a mean of the readings. And so that's why these readings are centered around 0. And we can take these readings and then determine the 2 sigma variation among them. And I have them listed here. So these readings are in bits. These are the bits that are coming off of the accelerometers. And you can see that the 2 sigma variation is a little bit different from each of them. Now we go on to the intrinsic properties calibration. And what you can see here is that the sensitivity of the X, Y, and Z accelerometers listed on the left side is about 1,630 odd or 40 bits per meter per second squared. The intrinsic properties can also be expressed in terms of a sensitivity matrix, and that's shown on the right side. The sensitivity matrix you could think of as what is more or less traditionally used for navigational purposes. And then on the below right, you can see what the sensor data sheet specifies. So what we can do next is we can take these sensitivities that I just reported for the X, Y, and Z accelerometers, and I'm reporting them here in terms of bits per meter per second squared. And then we can combine that with the uncertainties that we measured for the static situation where we had the accelerometers sitting on a tabletop. And these are the values that we have here. Now, if I take that information that I just showed, what we're looking at are 3 graphs here for the X, Y, and Z accelerometers. The first point is the intrinsic or static calibration. And those uncertainties are very small compared to the other 2 calibration methods that we have. shown here. The second one is the rotation implementation of the intrinsic static method, and this is at 0.5 hertz. And then we have our shaker at 1 hertz. And the uncertainties from the shaker are larger than the other two, because as we go down to lower frequencies, 1 hertz here, the signal to noise ratio becomes smaller and smaller. And so we are basically getting more noise with our measurement, and that starts to increase the uncertainties. But still, within their uncertainties, they're matching up with each other. Now, for the protocol demonstration, what we're doing here is we're taking the smart sensor, we've programmed it to transmit the data in an ASCII format. And this is in the columns that I show here. The first one is a timestamp in milliseconds coming from the sensor. And then we have 3 numbers in meters per second square for each of the X, Y, and Z accelerometers. And then along with that, we also have our uncertainties reported, which I'm calling UX, UY, and UZ. And those units are also in meters per second squared. So the accelerations, X, Y, and Z, are determined using those calibration factors measured using the intrinsic properties method, and then the uncertainties using that static set of measurements that I just showed. We also will be showing, in terms of this demonstration, another approach where we're looking at a 5-point moving average of the readings as we go along. So you could think of this as basically the point that we are at this time that we're reporting, and then we take the 4 additional points before it, so we can start to look at, what is the trend and what is happening with the signal as it's coming along. So here we have a program. This is the Labview program, and this is a movie that I'd like to run for you. And what you're looking at here basically is a accelerometer. This is the device, the smart sensor that I'm holding in my hand, and I'm basically rotating it around in my hand. And we're looking at one of the axes coming from the accelerometer. This is the z-axis of the accelerometer. And there are 2 plots that you're looking at here. So this is a real-time plot that comes out of the accelerometers as I'm moving them around. What we're looking at basically is on the left side is what's coming out from the Arduino or smart sensor. And on the right side is the same data, but now with a 5-point moving average that we're using as well. Overall, you can see that the results are fairly similar to each other. And what you're seeing is the measurement inside of an envelope. And the measurement then is basically what the accelerometer is reading, and the envelope is the uncertainties of the accelerometer that are being reported by the smart sensor. In the upper right, we're looking at these arrows that are moving around, and these basically are the vectors of the X, Y, and Z axes as I'm moving the device. And so it's meant to simulate, what I'm doing with my hand as I move this accelerometer around. Now we can take this kind of data and we can begin to take this uncertainty measurement from the data and apply it to different kinds of excitations, and then begin to compare what we can observe using other techniques to what the sensor is telling us. And so here in this example, I'm showing a pendulum exciter or pendulum excitation. And what we're doing here is we have a pendulum with a weight on the end that hits a block, and the sensor is mounted on this block, and we hit the block and the block will move and come to a stop. And so what we can do is start with measuring the starting distance of the block, and then we can have the impact and the block will move and then come to a stop. And so then we can measure this finishing distance, and the difference between those two is the distance traveled, how far the block moved. And so this is an example that I'm showing here of comparing the distance traveled for this kind of transient excitation. So what we're showing on the left then is the data that's coming off of the accelerometer. And then we can take that data and integrate it to get a velocity. And then the velocity can be integrated once more to measure the distance traveled. And so on that right side, I'm in the box that's in the graph. What you're seeing is that the accelerometer, after we integrate the signal, reports a measurement of 261.7 millimeters, while the distance traveled that we measured using a caliper is 265.6 millimeters. So we can begin now to take these results then and use the uncertainties that are reported by the accelerometer to understand whether the model that we're proposing here is adequate or whether further models need to be developed for the analysis and perhaps equivalent circuit as well that's more complex. So to summarize this report, we provided this demonstration of concept of a dynamic uncertainty communication protocol. And we demonstrated the idea using triaxial accelerometers. We calibrated these accelerometers using a static rotation angles, which we call the intrinsic properties calibration in the gravitational field. And then we used a dynamic uncertainty that was reported by the sensor in two ways. One way is using the standard deviation of the noise when the sensor is sitting motionless, and the other way was using a 5-point moving average approach. The demonstration that I showed here was presented using Labview to display the real-time acceleration measurements together with an uncertainty envelope. And our ongoing work is now to work on the comparison measurements with various modes of excitation to refine the dynamic uncertainty analysis. I think the takeaway that I hope we can discuss in this session is this idea whether if we can formulate an adequate dynamic uncertainty analysis at the edge, at the smart sensor itself, and communicate these measurements together with their instantaneous uncertainties, does that then mean that the sensor network becomes more adaptable? And so that therefore the host computers don't need to know or store the specific sensor performance parameters with them. Instead, the sensor is constantly reporting both the measurement and the uncertainty of the measurement, and then the host computer can take that information and perform whatever analysis it's doing to determine the environmental conditions at the sensor and what the sensors are reporting on the network. Thank you for listening to the presentation. I hope you found it interesting and something to think about, and I would look forward to any discussion that we have in this proposal.